So we have on the left side here a 0.25 inch square titanium cable. We're given that that goes from 50 degrees to 150 degrees. So the delta T will be 100 degrees Fahrenheit. On the right side, we have a 0.5 square inch steel cable. We want to find the stress in each rod and also the displacement of point A on the rigid bar. So by saying rigid bar, it means this bar is not going to strain at all. It's going to stay perfectly flat. So first step, always statics, draw a free body diagram. So we have a cable at A, this can be pulling up. I'll call that force A. And then the same thing for B, force B. We have a 51 kip load pulling down. And then we have a pin at C, so we'll have CY and CX. So we don't really care about CY, CX. We could find them if we wanted, but we only really care about force A and force B. So the one equation here that'll work and get us only those two unknowns are summing moments about C. So we're going to sum moments about C equals 0. It's a static system. So we have a positive 51 times 3 feet minus force A times 4 feet and minus force B times 2 feet. So we end up getting, simplify that down some, force B plus 2 force A equals 76.5. So that's one equation with two unknowns. So ideally, we only want to use one more equation with those same two unknowns. So we can do compatibility. So we know that it's going to stay locked at point C right here. That point's not going to move. But this side is going to be pulled down. So our triangle would end up looking like this. We know this distance right here, that is B, and this side is A. So this distance here that moves down, that is the change in B, and this is the change in length of A. So we can do compatibility, just similar triangles. So we know that delta B over 2 feet has to equal delta A over 4 feet. Which, simplify that down some, and we get 2 times delta B has to equal delta A. So that is relating A and B, but we want to relate the forces of A and B. So to do that, we'll have to plug in what actually is going on here for that delta. So in delta A, we have a force that causes it to elongate and also a change in temperature. So delta A will look like PL over AE, elongation due to the force, plus alpha delta TL, elongation due to the thermal load. And then for delta B, it's being pulled down or elongated by this force, and there's no thermal load. So that is just going to be PL over AE. So now we'll plug these in to this equation. So 2 times delta B. So P, the force, is just going to be force B. The length, that is this 2 feet. And we're going to go ahead and put that in inches. So I'm going to say times 24. The area is given as 0.5, and that's in inches squared. and our modulus is 29,000 KSI. And that equals delta A. So the PL over AE for that, we have force A. It is 3 feet long, so 36 inches. We're given an area of 0.25 inches squared. And the modulus is 17,400 KSI. And then it's also elongating to thermal load, so plus our given alpha is 5.2 times 10 to the negative 6. Our delta T is 100, and our length is 36 inches. So now we finally have two equations with two unknowns. So if we simplify this down, we get 0.00331 times force B equals 0.008276 times force A plus 0.01872. So now we have a system of equations. That's one equation, and this is our second equation. So solving for those, we get that force A will be 18.3 kips. I know it's going to be in kips because I used KSI for my modulus up here. And force B will be 40 kips. So, those are our forces if we are elastic. Up here, when we used PL over AE for both these terms, that assumes that they don't yield. So that's what we have to check. So the stress in A is force over area, 18.3 over the area of 0.25 gives us 73.2 KSI. That material yields at 134 KSI. So that is less than the yielding stress. For B, stress in B, 40 over the area of 0.5 gives us 80 KSI. That material yields at 36. Therefore, that is greater than the yield stress. So we're going to assume, and that yield stress is 36. So we're going to go ahead and assume that the most stress it can handle is at 36. So how much force can that handle? So force over that same area of 0.5 equals 36. So the most force that B could handle would be 18 kips. So now we need to see from this equation right here, how much does force A have to take now? So we said force B plus 2 times force A equals 76.5. So plug in that 18 for force B, and we get force A will be 29.25 kips. So now that we have that, we have to show that, okay, now we know that force A won't yield. So check again, force A, so stress in A equals 29.25 over the area of 0.25. And we get 117 KSI. And that is less than the shear yield of 134. So that's good. That means these are the answers for the forces in each cable. So now we need to find the displacement of point A, right here. So we normally use displacement as this setup. So we're going to plug that in. So displacement of A, or you can write like this, equals, we said, PL over AE plus alpha delta TL. So that P, that's the force in A. We found that to be 29.25. We know the length is 36. Area is 0.25. And the modulus is 17,400. Then plus our alpha, 5.2 times 10 to the negative 6. Our delta T is 100. And the length is 36 inches. So we get the change in length of A to be 0.2608 inches.